Hello, hello. It is lecture 21, or if your video slipped, 21. But you know what? Can you tell the difference between 12 and 21 in this case? I'll do it sideways. 21 or 21. Yes, lecture 21. A very, very exciting, very, very cool lecture. In part of the reason this lecture is so cool is because it's kind of like partly not me. In other words, the part that I'm going to be talking about for the so-called lecture 21 part is going to be comparatively shorter than previous other lectures because a substantial lecture that I want you to watch about this topic that we're going to be talking about will be delivered by another person who has made their video public, and I cannot wait to show you that and talk to you about it. In fact, you've already seen some of the videos by this YouTuber in other parts of the course. And I will tell you all about it, and I encourage you to look at it because it actually be a big part of it. So be ready for that. This unusual format for this lecture, and probably for the next one too, because I really like how she has done this particular covering of this material. Okay, so here is the deal. All right, we have talked in lecture 19 and lecture 20 about Hooke's law, about deformations, about restoring forces and energy in a spring and things like that. Well, here's the deal. We're taking that to the next cool level. And the story is this. People like Robert Hooke and others who followed after him realized that the kind of motion, the kind of periodic motion, the thing that happens on a regular basis with this kind of thing, when you have a restoring force, F equals minus kx, right? Well, this is much more bouncy than usual, but like if I just, like, kind of like that, right? Kind of this bouncing usual, it follows really interesting mathematical rules. And the interesting mathematical rules and the way that it works with, like I was talking about, like oxygen atoms and so forth, creating those rules made it mathematically so interesting, this kind of study, that this kind of oscillatory motion, this kind of periodic motion is worth serious investigation. And the discussion of it mathematically has become one of the most important and valuable things in all of physics. Okay, so it's really worth learning about. Now, sometimes it's harder to know exactly how it matches up with like biological systems, but it actually does matter. So these next lecture, maybe two lectures, will be more about general physics, but you will be able to see definitely how it applies to our lives. Because after that, in the next lectures, we're talking about how you hear because of these things, this kind of motion. But this kind of oscillatory motion that I want to tell you about for this lecture, like I said, I'm going to talk about half the length of the lecture because another person is going to talk the other half of the length of the lecture, and it's really cool. All right, so let's go right to the screen and explain what this kind of motion is. This motion is called simple harmonic motion. Okay, now let's go and let me explain why we are doing it this way. What basically happened was, as you saw in the previous part, right, the motion of the spring going back and forth, right? Here, this right now, we're at 16.3, simple harmonic motion, a special periodic motion. What happened was that you have this kind of motion is a really neat system where the net force can be described by Hooke's law. Okay, and why is it called simple harmonic oscillator? Simple because the force that's restoring it is very simple. It's F equals minus kx, right? It's directly proportional to the amount of distance that's been displaced, which is kind of cool, right? The other aspect, the reason it's called a harmonic oscillator is because you wind up creating harmonies. Yeah, you wind up being able to have these kinds of motions in such a predictable and interesting way that they oscillate in the same left and right or up and down always. And you have a same maximum amplitude, and then you depend on the kind of oscillation. So here's a basic example, right? We were talking about, I was using the spring earlier and like bouncing it up and down. Imagine if instead of bouncing it up and down, we're just sliding it back and forth on something that's perfectly smooth. It doesn't have any friction, ice thing or in an air track or something. You may have already done something like this in your courses. Now, what happens when you do that? This thing gets pushed in, pulled out, pushed in, pulled out at a regular basis. This is where it would ordinarily be, right? Your oscillation would kind of start there. Then you pull it out a little bit. It'll get to this point. At the moment that it reaches right? Its actual equilibrium point, which it would have been if you hadn't pulled it in the first place, right? That's actually when it reaches the speed that it's going at its maximum, right? Its displacement from its original position will be 0, and the force on it will be 0 because that's where it started, right? Equilibrium, but its velocity will be maximum. Cool, right? And then it compresses all the way down to the bottom and then comes back out again, right? And when it presses at its lowest point, notice how the displacement is maximum, the velocity is 0 at the end, and the force is maximum going in the other direction. And then that's basically comes back and forth the same way. So you have this sort of oscillation about simpleness and harmonicness, and it's really kind of neat, right? So there's lots of really neat things about simple harmonic oscillators. And one of the most important ones is it doesn't matter how strong you do this. The period, right? The frequency, they are the same. It doesn't matter if I pull it longer or if I pull it shorter, it will still be the same amount of time it takes. Let's try to see if that works demonstrated here, right? I'm going to pull this, okay, to have this thing, and if I just, here's the equilibrium point, kind of like right here. Okay, all right. Now, if I pull a little bit, 1, 2, 3, 4, 5, 6, right? So that's kind of about how fast it goes. What if I put a long bit? If the hypothesis is correct, then it should be about the same speed, even though I pulled it much longer. 1, 2, 3, 4, 5, 6. Amazing. It works. Wow. Now you notice the amplitude is getting smaller and smaller. It's true. But basically, the timing is the same no matter how big or small. That's harmony, right? That allows you to make harmony. Imagine you have some loud sound and you have a smaller sound and you have these kind of oscillations that are happening all in different things. And so you wind up with harmonics. That is cool. Turns out it's so beautiful and so awesome that a lot of things that oscillate in the world work that way. And it's really neat to see how that all gets put together. Okay, so now here is the key thing that I want to show you. And now we're going to deviate a little bit off of the college OpenStax college physics textbook for this reason. Okay, we are going to investigate and explain simple harmonic motion in a way that is not just you memorizing the formulas. As you know, memorizing formulas is useful, but that's not what I want you to do. I want you to understand the physics of it. And so as a result, I want you to see something very visual. And the visualness of this is actually very nicely displayed in the simple harmonic motion Wikipedia page. Take a look at this animation in the corner. All right, I'm sorry if it's small. If it's too small to see, go to the Wikipedia page of simple harmonic motion and see it yourself. Let me see if I can get it bigger. I have no idea if I can make it bigger, but let me give it a try. Aha. See, here's the picture. And this is an animation. All right, look what happens. This is a spring going up and down, right? Up and down and up and down. And if you look at the up and down motion of this thing, imagine what you're doing. The speed of it going up and down is exactly what the speed would be if you happen to be watching this piece of this green dot moving, right, in a circle, but at a 90-degree angle. So if I'm looking, in other words, this green dot is moving up and down at exactly the same speed that this green dot is moving up and down on, if this green dot is moving around in a circle and you're looking at it from the side, right? The matching of this is uncanny. It's remarkable. Going around in a circle and going up and down on a spring have the same mathematical expression for velocity, right? Same expression for the position. Wow, that's a harmony. That's a harmony. So you have that kind of relationship, which is so cool because then you realize, wait, when the planets are going around something, or when I'm spinning around, we're talking about angular momentum, right? And going around with in a circle, uniform circular motion back earlier on in the semester. Turns out that this harmonic motion going up and down is identical in very important mathematical ways. Cool, right? Yes, it is cool. And that's why I want you to understand more than just memorizing formulas about periods and frequencies, why this is true. The next part of this conversation is all about why that is true. And to understand why this works, okay, there's a lot of stuff that people have been working on for many years to explain. And what you need to know is the relationship between displacement, between velocity and acceleration. We've done that before, right? And I've mentioned many times the concepts of calculus. And I know that this class does not require calculus, and therefore I haven't put any calculus in the class. But it turns out that for simple harmonic motion, this is, first of all, so important in physics, and second of all, so elegant and beautiful, right, that I find it necessary for you to look at it from the perspective of how we understand it. And the way we understand it is the change in displacement as a function of time, which we call velocity, and the change in velocity as a function of time, which we call the acceleration. These relationships in the changes, the change of the change and things like that, okay, that is often referred to in calculus. Now, calculus, I know you guys are like, many of you are like, oh, calculus is cool, right? It's fun, it's neat. And then others of you are like, oh, calculus sounds a little bit scary, sounds like a little bit, afraid of stuff. It's not that bad. It's just, it uses weird letters and numbers. And sometimes, people who know calculus, oh yeah, well, it's really cool and important. And therefore you wind up like being a little bit intimidated by it. But because I don't want you to be intimidated by it, and because it doesn't really matter one way or another, whether you know the calculus, but as long as you know the concepts of things that are changing about it, okay, this is a mathematically useful thing for you to learn and to exercise your brain about. Bottom line, when you are doing something along the lines of this simple harmonic motion, because it's mathematically related to going around in a circle, right, with the spring force going up and down and things like that, you wind up being able to use your 2 pi radians, which I just barely referred to in the previous lecture, right? The omega over 2 pi equals the frequency kind of thing, right? And then the period, of course, is 1 over the frequency and things like that. Those numbers start coming into your calculations. And the seeing how it goes in your calculations is really elegant and beautiful. And I want you to see that. And I want you to see it in a way that I, with my limited production budget, cannot show you to my satisfaction. And that's why I'm going to take you to the next level on that. Okay, I'm going to share my screen again. We'll go to the College OpenStax physics textbook so I can show you what you will see there, okay, in chapter 16.3. We started looking at this, a special kind of periodic motion. And what happens is you get this period of simple harmonic oscillator. All right, you have a mass and you have a force. And then later on, you have some other stuff about simple harmonic oscillations. And so this is useful. Okay, it's good for you to take a look at. And then it starts to link between simple harmonic motion and waves, right? When a wave travels, like in the sky, or a wave on the ocean or something like that, right? Or basically, it travels up and down in simple harmonic motion. Yes, the up and down version of a wave traveling through is in many instances, not every instance, but in many instances in nature, has the same kind of motion as a simple harmonic oscillator, like a spring. All right, so it's really kind of cool. And I want you to understand this much better than this is explaining here in this textbook, because here in this textbook, all you're doing, for better or worse, is to memorize a formula. How useful is that? Useful, but not the level of understanding I want you to have. And then 16.4, the simple pendulum. All right, this is another example of simple harmonic motion in a special case. If you are swinging, remember we were talking earlier in the semester about angles and angular velocities, right? If you swing a pendulum in a small range, not a big one, in other words, the theta is relatively small, what happens is that the combination of the restoring force brought to you by the string in a pendulum and the force of gravity on the object that is swinging back and forth, the pendulum bob, also creates a simple harmonic motion situation. It's really kind of cool because of the relationship between sine theta, the sine is the trigonometric function, right, that you're familiar with, and the actual angle itself, right? The relationship is sufficiently close for small amounts of theta that it acts essentially exactly like a spring. But instead of the K, right, being the restoring the spring constant, you have this thing, mg over L, where m is the mass of the bob, g is the gravitational acceleration, and L is the length of the pendulum. So this is kind of cool too. So I want to get you involved in this and understand it. Realize that, you see, the period of a pendulum doesn't matter how heavy the bob is. It only matters in small oscillations how long the pendulum string is. It's the same kind of concept about it doesn't matter how far I stretch out the spring, right? It still has the same oscillatory motion if it's the same spring constant. Pretty cool, right? So anyway, this is really stuff that I just want you to see more of in the beauty of it rather than just memorizing the pendulum stuff. Okay, those equations, they're just memorization. What's the point? I want you to get it. And that's why we're going to go for the rest of this lecture to someone who has high production value, who has a very, very good way of explaining it, in my opinion, and has graciously provided her work for public consumption on the internet. Okay, so a brief introduction about that. I'll first go to the YouTube page for this person's stuff and in this particular thing. And I want to show that to you so that you'll be ready to see it. It is here, okay? This is the YouTube link. We'll put it on the study guide and everything. And remember, you're going to have to take notes on this video the way that you normally take notes on my lectures. Okay, but this one will be like part 2 almost of that lecture. So be ready to do the study guide in exactly the same way for this as you would do for my lectures, perhaps even better. And let me explain why this is so cool. Okay, this is Physics 101, basically a college level equivalent of Physics 1, but done in the advanced placement physics context for high school physics in the United States. All right, and the host is Diana Cowan. Who is Diana Cowan? She goes by Physics Girl. And like I said, you have probably seen her before. Okay. This particular video is just about 25 minutes or so. And it's got some cool stuff, sort of just context. And so because she does this as an entrepreneur, it's really, really high quality work. And she's been doing this for many years. Is very, very talented. Diana graduated from MIT in physics. So, she really knows her chops. But she also loved science so much that she didn't want to just sort of do it. She wanted to share it. So for her career, what she's done is created a career out of sharing physics with people, sometimes in strictly academic contexts, sometimes in very unacademic contexts, and sometimes in between. But in all cases, she's been able to bring to it a kind of energy and understanding and desire to express it the way that I feel I want to do things as well. She's done a great job in many, many ways, and I'm really, really glad to be able to tap that resource for this particular aspect of the course. Okay, so remember this for the rest of this lecture, right? You've seen some of the stuff that I've talked about, and then we're going to do that. You're going to see this, watch this lecture here on simple harmonic motion. There's going to be some calculus in it. And if you haven't been exposed to that calculus yet, don't worry about it. Remember, those symbols and stuff, not important, but the concepts are what important. The change in displacement, right, is velocity. The change in velocity is acceleration, which means that the change of displacement, what we would call in calculus the second derivative, is acceleration, right? And therefore, that concept of the change being related to the original displacement in the first place, right, is what makes simple harmonic motion so amazing and so beautiful. And I want you to see that explanation with the best possible graphics and the excellent animations that are available and the demonstrations that are there. Okay, so remember, at the end of this lecture that Diana Cowan gives, the Physics 101 on simple harmonic motion, okay, she's got the practice problems on there, and she's got some equations that are up on the screen as well. Those are the things you need to take away with you to make the calculations for simple harmonic motion. Okay, but what I want you to do is to see and understand how it works and why it works. So that's why it's really important to take notes on that aspect of things. Okay, that's the part that matters to me even more than the equations at the end, because the equations at the end you'll see anywhere. They're all over the place. But the concepts, get them. Okay, that's simple harmonic motion and it's worth learning. So please do that. Sound good? Okay, so fill out those study guides. I mean, there was some to fill out for what I just talked about here because I have gone through a few things, but I want you to go through that and do the study guides on that part and write your notes on Diana Cohen's simple harmonic motion lecture that's on the video. All right, and go to that study guide. Do the rest of the study guide as well. I hope you have a great time with it. Thank you so much. And we're going to get the simple harmonic motion going here in this lecture 21 on to the next lecture, which has to do with waves. Yeah, because I just mentioned them. We're just getting started. It is so cool. This is excellent physics stuff. Thank you so much for being here. Fill out all your study guide stuff. Any questions, of course, especially after you've watched the Diana Cohen video, all right, about simple harmonic motion. After you've watched that, ask me any questions you want. Ask your recitation instructor, ask your lab instructor. We will get really neat thought processes and insights about this stuff. Okay, thank you so much. See you again in the next lecture, all right? Thanks.